Open a map on your phone and a blue dot appears almost instantly. That feels normal now. The strange part is that nothing visible connects your hand to the sky. No beam, no pointer, no satellite camera staring down at your street. And yet a device in your pocket can work out where you are by listening to radio pulses from machines more than 20,000 kilometers above Earth. GPS looks like a map trick. It is really a time trick. Nothing up there knows where you are. The satellites are not watching you, not searching for you, not photographing your street. They are doing something far more boring and far more clever. They are broadcasting the time over and over and letting your phone work out the rest. Once you see that, the whole system changes shape. It stops looking like space magic and starts looking like one enormous, very precise clock. The first wrong picture to throw away is the simplest one. Satellites are not up there searching for you. They are not scanning the ground and tagging your location from above. GPS works the other way round. The satellites keep broadcasting and your phone listens. That matters because GPS is really three linked systems. There is the space segment, which is the constellation of satellites circling Earth. There is the control segment on the ground, which tracks those satellites, checks their clocks, and uploads fresh corrections. Then there is the user segment, which is the receiver in your phone, your car, or a survey tool. We tend to notice only the last piece because it is the one in our hand, but the blue dot exists only because all three are working together. Now, what are the satellites actually sending down? At the simplest level, each signal carries two things your phone desperately needs. First, where that satellite was when the signal went out. Second, the exact time the signal left. That is the whole trick in embryo, not a finished map, not a label saying you are here. Just position and time. The position part matters because your phone needs a known point in space to measure from. The time part matters because the signal is moving at light speed. If the phone can compare when the signal left to when it arrived, it can start working out how far that signal traveled. That is why GPS is secretly more like listening than looking. Picture a satellite above Earth throwing down perfectly timed pulses. Your phone catches one of them and asks one quiet question: how long was that pulse traveling before I heard it? The answer is tiny. Radio signals move so fast that the delay is only a sliver of a second. But tiny is enough. In GPS, tiny timing gaps are the raw material of position, so the map is not the first thing the receiver gets. The map is the final picture after a lot of timing work. This is also why the satellites carry atomic clocks. The whole system depends on astonishingly reliable timing. If the sent time is off, the distance will be off. If the distance is off, the position will be off. GPS is not a normal consumer gadget trick wearing a space costume. It is a clock system that happens to give you a location. Once that lands, the next step is almost obvious. If your phone knows when a signal left a satellite and when it arrived, how does that become a distance instead of just an abstract delay? Take one satellite and one pulse of radio energy. The satellite sends the pulse. The pulse races toward Earth at the speed of light. Your phone catches it a fraction of a second later. That travel time is the first real measurement GPS makes. Not latitude, not longitude, just travel time. Now turn that time into something you can draw. If you know how fast something moves, and you know how long it was moving, you can work out how far it went. That is the clean spine underneath GPS. The signal speed is known, the delay is measured. Multiply one by the other, and you get a distance. Or at least, something very close to a distance. This is why a GPS receiver is always doing a strange conversion in the background. It hears time and turns it into geometry. One little delay becomes one apparent range from your phone to one satellite. You can picture that as a huge shell centered on the satellite. If your phone is this apparent distance away, then it could be anywhere on that shell, not one point. An entire surface of possibilities wrapped around Earth. That is the part people often skip, and it matters. One signal does not reveal where you are. One signal only says you must be somewhere at that measured distance from that one known satellite. The neat technical word for that measured range is pseudorange, but it helps to delay the jargon because the basic picture is already doing the work. Your phone has not found itself yet. It has only drawn one enormous maybe. There is a nice way to feel how wild the precision has to be here. Light travels about 300,000 kilometers every second, so even a very small timing mistake turns into a large distance mistake. A millionth of a second sounds tiny in ordinary life. In GPS terms, it is enormous. Time errors stretch directly into space errors. That is why the story stays visual. One pulse leaves orbit. One delay is measured. One shell appears. The shell is the first hint that GPS is not a lookup table. It is a deduction, and now the next problem arrives immediately. If one shell still leaves you with countless possible places, how do you squeeze those possibilities down until only one location remains? Start with 2 satellites. If your phone measures an apparent distance to the first one, it can be anywhere on that first shell. Measure the apparent distance to a second satellite, and now your phone must be where those 2 shells overlap. That overlap cuts the possibilities down dramatically. Bring in a third satellite, and the geometry tightens again. Now the receiver is no longer floating across a giant surface of possible locations. It is closing in on a small set of answers. This is the part often drawn as a clean school diagram, with circles shrinking toward one point. The real picture is 3-dimensional, but the idea is the same. Several measured ranges squeeze the answer down. That is the moment many people think the problem is finished. 3 satellites, 3 distances, 1 location. Job done. But there is one hidden weakness in that neat story. The satellites have atomic clocks. Your phone does not. Your phone has a decent electronic clock, but it is not living in the same universe of precision as the clocks riding on board the satellites. If your receiver clock is even slightly off, every travel time measurement it makes will be shifted. And because those shifts are all tied to the same bad receiver clock, the measured ranges will all be wrong together. So now the receiver is solving more than a location problem. It is solving a location problem plus a clock problem. That is why the 4th satellite matters so much. With that extra measurement, the receiver gains enough information to solve for 4 unknowns at once: where you are across the surface, how high you are, and how far your own clock is off from true GPS time. The extra satellite is not just spare confidence, it is part of the actual answer. This is the real aha in GPS. The phone is not only finding a point in space, it is correcting its own sense of time while it does it. You can picture 3 shells that almost meet, but not quite. They are all being nudged by the same clock mistake inside the receiver. Then a 4th shell arrives and the whole solution shifts. Suddenly there is 1 position and 1 clock correction that make all the measurements agree as well as possible. That is why the blue dot does not come from one brilliant signal. It comes from a little negotiation between several signals and 1 imperfect clock. And once you see that, the name pseudorange starts to earn its keep. Those measured distances are useful, but they are not pure geometric truth straight out of space. They are apparent distances shaped by real clocks, real delays, and real imperfections. So even with 4 satellites, GPS still is not a perfect classroom picture. Reality keeps bending the lines. The measured answer still has to survive clocks, air, and reflections. By this point, the clean version of GPS is visible. Satellites send position and time. Your phone turns delays into apparent distances. Several apparent distances plus 1 clock correction become a location. Now reality starts interfering. This is where pseudorange becomes the right word. The measured range is not just a pure geometric distance from phone to satellite. It is that distance plus the messiness of the real system. Receiver clock offset gets into it. Satellite clock behavior matters. The atmosphere slows signals a bit. Noise sneaks in. Reflections can make a signal seem to travel farther than it really did. So the receiver is always working with a corrected estimate, not a divine line drawn perfectly through empty space. That does not make GPS flimsy. It makes GPS honest. And it also explains why the control segment exists at all. Those ground stations are not decorative support staff. They are constantly tracking satellites, checking their orbit data, checking their clock behavior, and uploading fresh navigation information. Without that upkeep, the space segment would slowly drift away from the nice, precise picture the receiver needs. That is a lovely hidden part of the system. Even the satellites that feel distant and autonomous are part of a maintained conversation with Earth. The control segment keeps telling them, in effect, here is your latest orbital truth, here is your latest timing truth, now keep broadcasting. Then there is the atmosphere. A clean classroom diagram shows a signal cutting through empty space like a ruler line. But real signals have to pass through layers around Earth that can delay them. The delay is not huge in human terms. In GPS terms, it matters. Remember, tiny timing slips become distance slips very quickly. Then there is multipath, which is one of the most visual failure sources in the whole story. Instead of reaching your phone along one clean route, a signal can bounce off a building face or another surface before it arrives. Now the receiver hears a path that is longer than the direct one, and the apparent distance stretches. So the neat shell picture is always being tugged around by small distortions, clock offsets, air, reflections, and plane measurement noise. That is what GPS is really doing. It does not solve with perfect distances. It solves with disciplined, corrected, imperfect ones. And now the most famous clock twist in physics finally makes sense here. Einstein is not a fun side note attached to GPS. He is already inside the timing budget. Relativity sounds like the sort of fact people bolt onto GPS to make it sound grander than it is. In reality, it belongs here naturally because GPS has already taught us the key lesson. Tiny timing differences matter. If a very small clock error can become a large distance error, then anything that changes clock rates is a practical problem, not a trivia question. GPS satellites are moving fast relative to Earth, and they are also much farther from Earth's gravity well than clocks on the ground. Those two conditions pull clock rates in opposite directions. Motion tends to make the satellite clocks run slower. Weaker gravity tends to make them run faster. The important part is the net result. Without correction, the satellite clocks would drift by about 38 microseconds per day relative to clocks on Earth. 38 microseconds does not sound frightening, it sounds microscopic. But GPS does not care how small it feels in speech. GPS cares how far light travels during that era. And light travels far enough in that time to turn a tiny clock drift into a giant position mistake. That is why relativity in GPS is operational. The system cannot shrug and carry on. The timing model has to account for those effects or the whole location answer degrades rapidly. This pays off the whole mechanism's spine. We began with a blue dot, then came timed signals, then came receiver clock correction, then came apparent ranges instead of perfect ones, and now even the satellite clocks themselves need a physics-aware model because space and motion change how time behaves. So Einstein enters the story at exactly the right moment. Not as decoration, as maintenance. You can picture two clocks that began together. One stays with us on Earth, one rides a satellite high above. They do not keep pace automatically. GPS works because the system knows that and corrects for it. That is also a good reminder that the word satellite can make things sound simpler than they are. These are not just radio boxes in orbit. They are precision timekeepers embedded in a continuously corrected physics problem. And if the answer depends on all of that care, then the final question becomes wonderfully concrete. What does it look like when some part of the timing story goes wrong in everyday life? Most GPS failures stop looking mysterious once the mechanism is in your head. Take the easiest case first. Go indoors, move under heavy cover, or stand where only a slice of sky is visible. Your receiver simply has less to work with, fewer good signals reach it. The clean geometry weakens. The answer gets less stable. Stand in the middle of a city full of tall glass and concrete, and a different problem appears. Signals can bounce. One pulse reaches you directly. Another version of that same pulse reaches you after reflecting off a building. Now the receiver has to sort out which arrival is the honest one. If it leans on the bounced path, the apparent distance grows and the position can slide. That is multipath, and it is a perfect example of GPS failing for a reason you can actually picture. Then there is the atmosphere again. Even without dramatic reflections, the path from space to your phone is not a vacuum tube. Signal delays through the layers around Earth can shift the timing just enough to matter, especially when several small errors start stacking together. And then there is interference. Radio systems work only if the receiver can hear the real signal clearly enough. If other radio energy swamps the band, or if deliberate jamming drowns the signal, the receiver loses the clean timing information it depends on. You do not need a geopolitical documentary to understand that failure. GPS is a listening system. If the listening gets corrupted, the answer gets corrupted. That is why jamming is best understood as one member of a larger family. It belongs beside blocked sky, reflected paths, and delayed signals. All of them damage the same core operation. They make the receiver worse at turning arrival time into trustworthy apparent distance. Spoofing sometimes appears in conversations about GPS too, but the main lesson does not need it. The securely grounded set is already enough. Obstruction limits the signals you can hear. Multipath distorts the path length. Atmospheric effects add delay. Interference makes the signal hard to hear at all. Each one attacks the timing story from a different angle. Now the whole system comes back into focus. GPS is not one magic beam from orbit. It is several timed broadcasts, several apparent distances, one clock correction, ongoing orbital maintenance, atmospheric modeling, and a constant battle against messy real-world conditions. Which is why the blue dot feels so effortless only when an enormous amount of invisible work is succeeding at once. Go back to that ordinary moment of opening a map and watching the blue dot settle onto your street. At first it feels like a location machine. Something in your pocket somehow knows where you are from space. But the deeper picture is better. GPS works because satellites keep sending out exquisitely timed signals about where they are and when those signals left. Your phone catches several of them, turns those tiny delays into apparent distances, corrects for its own imperfect clock, and solves where it must be. That is why 4 satellites matter, why pseudorange matters, why ground stations and relativity both earn their place in the budget, and it is why tall buildings, bad reflections, weak sky view or interference can all break the spell in ways that suddenly make sense. GPS does not see you on a map. It hears time from space and turns that time into place.